The next circuit I want to talk about is the inverting amplifier. This is the first time we're going to add a couple passive components around the op amp. You can see that this particular configuration has feedback running through a resistor, which I've labeled RF for the feedback resistor, into the inverting input. So this is negative feedback. And in this case, our input voltage coming into the op amp is also running through another resistor, which I've labeled R1 here, to get to this point. So I just want to talk a little bit about what negative feedback is. Negative feedback is any sort of feedback mechanism which tries to restore something towards equilibrium. In the case of the op amp, what we're trying to get towards equilibrium are basically these two inputs, the non-inverting input and the inverting input. So what the op amp is going to try to do is to adjust V out to get these two things as close together as possible. Now the non-inverting input is connected to ground, so that means it's going to adjust the output to get this input to be as close to ground as possible. So how is it going to do that? Well, remember that it can adjust this voltage. That'll cause a current. That current will flow through here. It won't go into the non-inverting endpoint. This is high impedance, or to the inverting endpoint. This is very high impedance. So the current will basically go straight across here, or the other way, flow in one of those directions. Now what does this look like? Well, this looks like our voltage divider right here. So we know what our input voltage is, or we'll set an input voltage. This is going to be approximately 0, so we can calculate the current across this resistor. That will be the same as the current across this resistor, because the current is going to flow through both resistors. And so that should tell us what the output voltage is. And if we solve, we can find out that the output voltage is equal to minus, hence this is why it's inverting, the resistance of the feedback resistor divided by the resistance of the input resistor times Vn. So I've set up basically a system with the feedback resistor at 100 kiloohms and the R1, the input resistor, at 47 kiloohms, so that I can get this to be approximately 2. So let's take a look at it on my breadboard. Here it is. This orange wire is connected to the output, which is connected through this 1 kiloohm resistor to the inverting input, and then there's a 47 kiloohm resistor basically connecting the inverting input over to this yellow wire, which is coming off of my potentiometer. I've grounded the non-inverting input with this gray wire. It's connected to the ground rail. And let's take a look. Right now my red probe is set to read the voltage coming in from the potentiometer, and that's right at 1 volt. So what we expect is that if I measure the output voltage, it should be close to about 2 volts. So let me move my probe here, hook it onto this orange line, which is connected to the output, and lo and behold, we're at -2. I forgot the inverting part. Positive 1 volts is going to lead to -2 volts output. This is, after all, an inverting amplifier, so that negative sign right in there is very important. And this is very useful, a very useful circuit. If you set the input resistance to the feedback resistance, you get basically a voltage inverter. If you put positive voltage in, you'll get a negative equivalent voltage out, and vice versa. So this is a really useful circuit to use, and another example of the op amp circuit. The next circuit I want to talk about is the non-inverting amplifier. This is very similar to the inverting amplifier. The only thing that's changed is, instead of putting V in into the first resistor, I'm grounding that, and I'm connecting V in to the non-inverting input. So you still have the feedback resistor, VF, and what I called before the input resistor, I'm now just calling it R1, it's a resistor. It's still acting as a voltage divider. So the negative feedback here is going to try to work such that, or the op amp is going to try to make it such that V out is high or low enough to make the non-inverting or the inverting input voltage equal to the non-inverting voltage. So if we're putting V in here, we expect that this output will do what it can to make this input also equal to V in. And we can calculate if this is ground, this is the potential V in. We can figure out how much current is going through this resistor, and that'll be the same amount of current that goes through this resistor. So doing the calculation, we find that V out should equal 1 plus the ratio of the feedback resistor divided by R1 times the input voltage. This is a very simple relationship. I've left in our circuit, basically all I've changed in our circuit is I have taken the output from our potentiometer, which is at 1 volt, put that into the positive or the non-inverting input of our op amp. I've taken the ground wire, which was gray, and I've connected that to the end of our 47 kilo ohm resistor. And then I still have the 100 kilo ohm resistor going between the output and the input. So I've hooked up the probe to the non-inverting input pin, so we can look at the voltage coming in, and it's still at 1 volt. So what we would expect, since RF over R1 is about 2, we would expect an output of about 1 plus 2, or 3 times the input, or 3 volts. So let's move the probe over to the output pin, and sure enough, we're getting 3.12 volts. So it's working pretty well. It seems to be right on target with our expectations. And this, the difference is, one, this amplifier is not inverting, so you put a positive voltage in, you get a positive voltage out. The other thing is, using these two resistors, we get slightly more boost. The amplification factor, RF over R1, is you add 1 to it. So instead of, in the previous example, we had inverting, so we got a negative voltage and about 2 volts. In this one we have 1 plus 2 times the input voltage, so positive 3 volts. The next circuit I want to show you is the Schmitt trigger. Now this is a little different than some of the previous circuits we've had. Previous circuits we had negative feedback. That is that the output was somehow feeding back into the inverting input. In this case, we're going to have positive feedback. That means the feedback going through a resistor in this case is going to the non-inverting input. So what's the difference between negative and positive feedback? Well, negative feedback is restoring. It moves a system towards equilibrium, whereas positive feedback moves a system away from equilibrium. A good physical example would be if you imagine a ball on the peak of a hill and just balancing right there. If you push it in either direction, it's going to roll down the rest of the way, accelerating down towards the edge of the hill. So that's an example of positive feedback. A slight displacement is just going to push the whole thing towards one end or the other. So in this case, V out is not going to do what it can to get these two inputs as close together as possible. V out is basically going to be pushed to either the positive limit or the negative limit, depending on what the value of the non-inverting input is. So let's consider this. In this case, the inverting input is set to ground. So if the non-inverting input goes above ground, this is going to go right up to the positive source voltage. If it's below ground, the output's going to go straight down to the negative voltage. So what do these two resistors do? Well, they still act as a voltage divider. So basically, based on the input, you can figure out whether, and based on the output, is this plus 5 volts or minus 5 volts, or whatever it happens to be, whatever the limits are, can you figure out at what point this is going to be 0, is going to be ground, and that's going to be the point where it flips. Well, it turns out in this situation, if we assume that this output can go full range, that is to plus Vs as its positive limit and minus Vs as its negative, then what we're going to find is that the threshold at which it changes is going to be resistance 1 over Rf times Vs if this output is at minus Vs. And if this is plus Vs, then we're going to get minus R1 over Rf Vs. These are the thresholds that it has to go through. So you notice the threshold changes. If this is negative and you're on your way up, you have to get to a much higher voltage in order to trip this and make it positive. If it's already positive, you have to get to a lower voltage to make it negative. And actually, that's how the Schmitt trigger works. So let's look at this graphically, because it might be a little bit easier to understand. And let's assume we start here. The x-axis is our input voltage, and the y-axis is the output voltage. Let's start with the input voltage as a low value, and the output voltage is a low value. So what we do is we turn up the input voltage, and we're going to find we can go up, 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 and we hit this threshold, and boom, the output voltage goes to its positive limit. So it's kind of like it just switches on like a step function there. And then we can continue raising the voltage. The output voltage stays at its maximum. As we drop the input, it doesn't immediately drop down. It actually goes further, follows this line until boom, hits this negative threshold, and then the output voltage drops down to a negative value. So this sort of pattern, where you have to pass a higher threshold to make it positive and a lower threshold to make it negative, is known as hysteresis. And this is useful if you're designing something like a thermostat. Let's say the input voltage is related to temperature, and this voltage here, it relates to the air conditioning, say, being on or off. And you wouldn't want that to switch at a very specific level. You wouldn't want it to be like 78 and it switches on, and go back through 78, it switches off, or 72. Because what you would have is the air conditioning system would switch on and off and on and off and on and off repeatedly. So you want a little gap here so that it goes through a temperature of, say, like 73 degrees. The air conditioning switches on and stays on until we drop down to a temperature of, say, 71. This keeps your electronics from, self-destructing by being turned on and off over and over again. And it's useful for several applications. So let's look at a circuit. So I am using a circuit now with, I've set up the Schmitt trigger on the top. I'm using my 100 kilo ohm resistor for RF and my 47 kilo ohm resistor for R1. So the threshold voltage is going to be roughly half the edge-to-edge voltage. I've actually wired my potentiometer into the other op-amp running as a voltage follower, just because there was current kind of running through from one system to the other, and I wanted to decouple it. And on the output, I've put an LED, and the LED is basically connected up to the negative voltage source. So when the op-amp is in the negative VS, negative voltage out, the LED is off. When it switches to positive, the LED turns on. And I can look at the input to the input voltage of my Schmitt trigger and kind of watch it as I turn it up, see how the system reacts. So I'm going to try to kind of go slowly. See, I'm going up. And I expect when I get to about 2.5 volts, the LED should turn on. So let's see how well that works. Okay, about 2.5. Later it's like 2.4 volts. And if I continue to raise the voltage up, it stays on. Now on the way back down, I think we have to remember this is not an ideal op amp. The voltage of the output is probably around 3.8 volts. So on the way down, we're actually, I think, not going to get to negative 2.5 volts. We're going to get more to like negative 2 volts. And then it should turn off. But you can see we go back below 2.5. It's still on. Drop down to 0 volts. The LED stays on. We're still in this hysteresis zone where it doesn't turn off. We have to get much lower to turn it off. Then we get down to minus, it turned out to be minus 1.5, and the LED turns off. And we can keep going down, the LED stays off. So that is a Schmitt trigger. It has a zone of hysteresis so that you don't have constant switching on and off of your LED. Or whatever electronics you have hooked up to it. And it can be used as a clean switch.